I would like to call for the first presentation Professor Marko Ignjatović. Professor Ignjatović is an associate professor in the University of Nice, Faculty of Mechanical Engineering, involved in the educational process at all levels at the faculty. 15 plus years of experience as expert consultant and energy auditor in energy efficiency projects. Starting from 2015 overseas faculties district heating systems serving more than 120,000 square meters of residential, educational and commercial buildings. Today, Professor Ignjatović will present a very important topic, which is impact of masonry block type of on energy performance of office building equipped with low temperature radiant system. Please acknowledge. Please close the microphone.
Okay. Thank you. Good morning. Before I start, I would like to thank my friends from ASHRAE Hellenic chapter for inviting me here. Also, I would like to express best regards from Serbian Society of HVAC, and also on behalf of ASHRAE Danube chapter members, which I'm part of. Today's topic is impact of masonry block type wall on energy performance of one office building. And this study was done by myself and my colleague Goran Vučković from the same university. We all know that buildings are central place of most human activities, whether we live, work, or do our conferences and other things. We spend most of times indoors. And in order to separate us from outside conditions, Sorry. And in order to separate us from outside conditions, we must use energy, and most of this energy is used in our HVAC systems. These are the data we had from EU level. In Serbia, the things are even worse, because according to some of our energy balance, more than 50% of final energy in Serbia is used in residential buildings, and also a lot of this energy is fossil fuel based, whether electricity or natural gas or some other fossil fuel. Considering building fund, there is a general conclusion that in Europe, on average, 3 out of 4 buildings are inefficient or underperforming, according to some national legislations. And also, with all the strategies involving building renovation, deep renovation, etc., on government or local level, there is only 1% of annual renovation rate considering building stock, whole building stock, and turnover rate is less than 1%. So basically, if we stop constructing buildings only in 100 years, considering today's tempo, we can refurbish all the buildings, and we know about the building life cycle and how much more energy is needed in this time period. So when we construct new buildings, we must take long-term impact, because they will remain for many years after they are built. In Serbia, as in most in Europe, we have a common approach. The basic one is to define maximum U values of building envelope parts. In this case, we do not consider layer sequence. It's the same whether how you put your layers on, and we do not consider thermal mass. Why is this property important? Because all the materials used in construction and within building can store and release heat. And if we know how to store and release, we can achieve some additional energy savings. And considering this thermal mass, we all know we have heavy mass buildings or low mass buildings. They have all their advantages and disadvantages. And using higher thermal mass can shift peak loads from during summer towards colder days, parts of the day, during night. In cold climates, it's basically the same, but there are some studies that show that this is not always the case. So basically you can increase energy consumption with higher thermal mass if you put intermittent operation on heating system, for example, which is the case in Serbia. One of my colleagues 10 years ago published an article considering impact of thermal mass on peak load, whether cooling or heating load, and he showed that not in all cases you can reduce peak loads with heavier buildings. So basically you should take consideration into particular building on each time. In Serbia, we traditionally use clay blocks to build our buildings, especially residential buildings, single or multi-family. And we don't treat thermal mass at all, although when I speak with architects, they know all the advantages of using thermal mass, whether it's a thromb wall or increased thermal mass on the outside, but we cannot calculate it. Like I said, when we treat U value, we have only steady state conditions. We have outside design conditions, inside design conditions. We don't do one calculation at one point in Serbia. And we completely disregard thermal inertia, which can be described with these two parameters. The first one is time lag, and the other one is decrement factor. Time lag or dephasing shows the time needed to propagate heat flux from outside surface of the wall towards inside. And decrement factor shows you the ratio between maximum and minimum surface temperatures on inside versus outside. In literature, there are various definitions of time lag. So, but the most common approach is that you look only into 24-hour period, and you just, how to say, identify times when there is peak inside surface temperature and peak outside surface temperature, and these, according to these classifications, you can calculate time lag. So it can be more than 24 hours or less. So the basic idea of this study was to calculate the potential impact the increased mass on the inside surface of the building could have on energy performance. In order to do that, with my colleague who, how to say, applied for patent for this increased mass block, we developed a two-way study. One was to focus on these dynamic properties, time lag and decrement factor, and the other was to compare this hypothetical new block with commercially available blocks on this office building in Niš. Most of you heard of Niš. I don't know how many of you visited. Niš is the third largest city in Serbia. It's in the southern part, 4 hours drive from Thessaloniki towards Belgrade. And it has a climate which is a bit, how to say, strange compared to the literature-based ones. You have extremes of 44.2 in the summer and minus 23.4. I remember this summer extreme. It's an official meteorological recording. It was in 2007, and on various city sites, due to heat island effect, it was more than plus 50, and all the chillers or heat pumps which were in operation were cut off during this peak temperature. One comparison, for example, with Thessaloniki, on 20-year average, if you put outside temperatures within pre-specified temperature bins, and you compare how this relates to outside design conditions. For example, in Niš, the outside winter design condition is -14, and on average we have only 10 hours below this temperature. But during summer operation, we have +35 outside design condition, and we have more than 200 hours per year on average above this temperature. And I must say, all systems within the Niš area are designed towards these two outside conditions. And what is the paradox? Besides commercial and public sector, in residential sector, you don't have cooling on your priority list at all. Because it's easier to build, we must follow our legislation considering only heating period, and then we put split air conditioners everywhere. So it's a bit strange, but this is the effect. So in order to calculate time lag and decrement factor, we used this building with defined building envelope thermal properties, and we did a twofold study. So basically we took 5 commercially available blocks in Serbia. They're all with the same thickness of 25 centimeters each, and then we created a hybrid We created a hybrid because we took 19 centimeters of the best block. We said, okay, we will scale it down, put it in the wall, and we will add 6 centimeters solid brick on the inside, and to see what happens. In order to do so, we developed 14 different scenarios, or even more. We used these commercially available blocks. We put everywhere around the envelope, and we then added insulation, which is the common practice. In Serbia, the bold values are below what is minimum defined by our national legislation. So, for example, a lot of these, which were built in 20 or 30 years ago, do not fall within this energy efficiency requirements now active. So our block with no insulation has a U value that can satisfy our national requirements. So we put for decrement and time lag calculation, we put ideal load conditions. We put constant heating and cooling set point indoors, and we neglected all internal loads in order to have the net influence of this increased block. I must say that this is not a standardized procedure. There is a special ISO standard covering these thermal inertia parameters, but we wanted to check how we can use energy performance simulation to calculate for typical building, its orientation and surroundings, how can we calculate these parameters, because everything you need you can generate as outputs from simulations. We prepared custom weather file for city of Niš. So basically we took a random day in January and July. We created artificial January and July with each of these days repeating one after another, and then ran the simulation for the following week. And all the data given here are averages. This is first part of the study. Second part is that we can apply, we wanted to check commercially available blocks with added insulation and this new type of block to see how it affects energy performance of the building, given on the previous slide. And on this table, you see there are only six wall types. They have similar U values. Our new block has the lowest, or let's say the worst U value for the experiment. And we developed two demand-side systems. One is a variable flow floor heating system. The other is traditional fan coil system. They have priority switching between seasons. So basically, during winter, only floor panels have the primary effect, and during summer, fan coils are primary during occupied hours, and floor panels are used in unoccupied hours. Since this is a commercial building, we try to replicate schedules from the building in the model. So the systems were unavailable from Friday 10 p.m. until Sunday 10 p.m. In these 2 days, we had no energy consumption in the building. These are simulation setup parameters for energy class. Our idea was to see how these floor panels would impact energy performance when we increase the thermal mass on the inside of the building. And it was set up that if indoor temperature within some zone is not met, then we go with full power, and then in the next 2 degrees centigrade we vary it by 0, or we vary flow towards zero flow. These are the results of the first part of the study. So in this table, for all wall configurations, different wall configurations, we calculated average decrement factor and time lag for summer and for winter week. We see that our new hypothetical block has the values that coincide with the values of other commercially available blocks. If we plot it against specific mass of the wall, we see the values correlate well. But what is most important is the following. These are averages for a week without considering orientation. When we look into orientation, we see the same values averaged over 7-day period, but with different orientations on cardinal direction. So we see that during the summer there is a strong influence, winter, strong influence on the northern decrement or northern orientation, and then it pretty much the same for other three cardinal direction. Why is this important? I'm a mechanical engineer, and I have a lot that my faculty shares the building with the faculty of architecture, and I collaborate with a lot of architectures. And when we discuss, they say, look, we can make buildings with different walls. It's important that outside they are the same visually. So if you show us that we can put something on the north which is better, considering energy efficiency, we can do it. It's they don't have boundaries considering this influence. They will put what they think is the best solution for this building. Considering energy performance, so with all the simulation setup described earlier, we took 6 wall configurations, and we used as a base case the wall with the smallest U value. It's the wall W4, and we see that, for instance, our wall W6 with increased mass has significant savings in energy consumption for heating operation, which is, most important in Serbia at the moment. it can lead up to 4%, actually it's 3.65 decrease. In this part of the study, we didn't focus on summer conditions because this block was intended for residential buildings, especially single family or 2 or 3 family buildings, not for high-rise buildings. At the end, to repeat that we traditionally use blocks when we build our houses. We can make more energy savings by increased thermal mass on the inside. In this study, we didn't focus on wall radiant systems, which can prove even more efficient. We focused only on what was built inside this commercial building, which is on operation for 2 or 3 months. What is the most important, although we didn't have the lowest U value, we still managed to have some energy savings, which are, I repeat, for Serbia, only focused currently on heating period, unfortunately. This block type is no more hypothetical because my colleague, Goran Vučković, applied for the patent. It's, I believe it's approved by our patent office. And he also managed to make a contract to create several prototypes in order to test mechanical properties, and then we will test thermal properties of this proposed block type, because we had satisfying results in this, how to say, numerical experiment. The building shown on this slide is the first and currently only A+ building according to Serbian legislation in my city, and both me and Goran Vučković, we were consultants on a pro bono basis because investor wanted to have the A+ building according to our legislation. The building is finished in November and it started running. So hopefully next time here we can put the actual energy consumption data here to see how it fits with our assumptions. And the good thing is that it's an IT sector building, and the investors want to have nearly zero energy building in operation. So they added additional systems on their building in order to make it nearly zero energy building, although it's not a requirement from our government. Thank you for your attention. I was a bit short. I expecting a 15-minute presentation. If you have any questions, I would love to answer.
Thank you very much, Professor. Very, very interesting presentation. I kept some notes, but it's really interesting, and I think it's the whole idea you presented is very, very much aligned with the sustainability rules, since the cleanest energy is the one that never consumed. So, before the questions, I have one question. Important, in my opinion, the cooperation between architects and engineers, mechanical engineers. We need to broaden these cooperations. You mentioned in the very last words that it is an IT sector building. So its operational costs and the operational conditions are running all the year.
Yes.
So regarding the temperatures that the typical, let's say, HVAC systems, the fan coils or the floor radiant systems, do you have any other suggestions? So let's say increased temperatures for cooling or decreased temperatures of water for heating? Is it affecting the typical HVAC systems?
Yes. I don't have actual data because the system or the building is running from mid-November. But I can say because one of my colleagues was a designer of HVAC systems, and I don't know whether it's the case in Greece. In Serbia, they they try to oversize everything to keep safe. Actually, besides this, they put additional system. It's an air-based system only to have it for a dew point control in summer operation. We didn't have summer to see whether this system will operate because floor panels temperature will be set higher than what is usual in order to decrease the on-off of this auxiliary air conditioning system. So we will see what will actual data show. What is the most important is that, for example, when they did the calculation, which is required by our national law, they doubled it in calculation step. And I said, what's the problem? They said, look, what is the internal load of here? And I see that the building has maybe 50 occupants, and they put all 50 in every room. And I said, why are you doing that? The software requires. Yes, the software, but you can schedule whether these 50 people will be in this room or what fraction of it will be. Make adjustments to your calculation. You cannot say software calculated something and then we will give our investor double the investment. So basically we try to keep this at minimum, and hopefully it is a very low, how to say, specific heating energy requirement. In summer, our models show it will be double. So it's not an easy task to make it zero. It's very hard. For winter period, no problem. Because our legislation, if you put 100 people in this room, they said, sit here for 2 or 3 days, you will have zero energy consumption. We all know this is not a fact.
Okay, thank you very much. Any questions for Professor Ignjatović? Just a moment to take the microphone, please.
Thank you for your presentation, Professor. I would like to ask you if you found any correlations among decrement factors, thermal lag, and the HVAC sizing.
No. We put, how to say, the building itself as an initial idea, and all the models were very well insulated, how to say, and all the U values you saw on the tables are far less than what is a minimum requirement if the investors wish. So basically, we have enough floor area to put radiant system, and it can keep, how to say, to maintain indoor temperature. I looked for several cases to see how this peak load compares. I didn't show it here, we didn't publish it. It was maybe in the range of plus minus 5% on average. It's no big deal. It doesn't influence peak load, if this was your question.
Thank you.
Any other questions? Okay, thank you very much, Professor.
Thank you.
Thank you very much.